yesterday, the last thing we did was doing a tremolo effect, right? So we're going to do a little bit more work on the tremolo effect, and then we'll make sure that everyone here is able to compile it as an audio unit plugin usable in GarageBand on a Mac computer. But first, we're going to do a few modifications to it so that it's better. So what I'm going to do is just go in here, Faust Workshop Day 2. So I'm going to create a new file for today. And I'm going to call this file d2.dsp, and that's the file that we're going to use today to work with. And yeah, I sent you an email last night about the website that was updated. So Faust Workshop, so I'm going to go on the website, scroll down. Yeah, and here is the last thing that we did yesterday, which was the tremolo effect. There we go. So I'm going to paste it in here so that we just start with what we left yesterday. And I just realized this morning that I forgot to put the imports filter.lib and import music.lib in here. So I'll have to correct that, but we should add them in here. Otherwise, it's not going to work. So I'm going to import music.lib and import filter.lib. There we go. Remember, I think we had a noise generator in here for the testing. Okay, so I'm going to save that. I'm going to start Faust Live. And I'm going to create a new default window, and I will drag and drop d2.dsp in it. There we go. I do get audio. I'm going to send that to the 2 speakers in the room because that's better. But of course, Jack didn't do the connection, so there we go. Tremolo, very good. So it works. Okay. So with tremolo, we can do other things. The tremolo effect is called a tremolo effect as long as the frequency of the modulator, which is a sine wave here, okay, is between, well, 0 something and let's say 15 hertz. The thing is, if we increase the frequency of the oscillator and we go above 20 hertz, at some point our ear, well, more like our brain, can't really make the distinction between all the oscillations because it gets too fast. And we basically get into the human hearing range that starts at 20 hertz, right? And then at this point, we get an interesting effect, which is called amplitude modulation. That is used a lot, well, to transmit data, for example, but also to make cool sound effects like ring modulation. So ring modulation and amplitude modulations are basically the same thing, okay? So what does ring modulation do to the input, to the incoming sound? So we're going to look at that. And to look at that, instead of sending noise to the tremolo, which is not going to be a tremolo anymore, I'm going to send a sine wave, okay? I'm going to give it a fixed frequency that is going to be 440 hertz, okay? And I'm going to send that to my tremolo effect. So, okay. So So far, nothing very interesting. So to make the whole thing better, I'm going to open my spectrum analyzer. And we're going to look at the spectrum of the sound generated by this object in here. Okay. So for now, well, we only have one sine wave, right, which is the sine wave that I'm sending to the tremolo effect. And I can see that the amplitude of the sine wave is changing over time. Like, whoop, 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 whoop. Okay? Very good. So I'm going to change the Faust code so that my slider is not between 0 and 15 hertz anymore, but between 0 and 1000 hertz, which is a lot more. Okay, and I'm also gonna change the frequency of my sine wave so that it's at 1000 hertz because it will be easier to see in the spectrum analyzer. Okay, so the maximum value of the slider is now 1000 hertz. And the frequency of the sine wave is 1000 hertz. Okay, so I save that. Now the changes should be applied. Okay, well, as I can see now, the sine wave is higher up in the spectrum here at 1000 hertz. Okay, if we listen to it, it's probably not very pleasant. But still okay, that's reasonable. Okay, very good. So I'm going to keep it like that for now. And now I will slowly increase the frequency of the tremolo, okay? So, actually, there we go. I'm going to do it here. That will be probably better. So I'm going to put it to 15 hertz, okay? So we can still only hear one sine wave, and we just see that the vibrations are happening faster. But what happens if I put the frequency to 50 hertz? Now it's getting a little bit harder to distinguish between the vibrations. What depth do you have? What depth do you choose? Depth maximum for now, so 1. Okay, and now I'm going to go even more crazy. I'm going to put 200 hertz. Oh, look at that. Now I have 3 sine waves. Okay, so that's the result of amplitude modulation. Okay, so the original sine wave is the one at the middle. Okay, and the 2 sine waves on the other side are called sidebands, and they are the result of the amplitude modulation. Okay, so if okay, so what is going to happen is that the higher this frequency here is going to be, the further apart the sidebands will be from the center frequency. Okay. So so if I change that by hand, I can see that the 2 sidebands are moving further apart from the center frequency, and I can draw things. Okay. So I don't know if you noticed that, but the side bands that we have here have an amplitude that is lower than the center frequency. Okay, so what happens is that the energy of the sine wave that we're sending in the tremolo effect. Okay, well, for instance, the energy of it is, well, the amplitude of it is 1, right? Because we're not scaling its amplitude for now, right? So so it's maximum amplitude. But what happens is that the energy contained in the sine wave gets spread out in the spectrum. Okay, so while without the tremolo effect and without the ring modulation, all the energy was concentrated on the center frequency. Now it is spread between the center frequency and the 2 sidebands. And the rule is that the center frequency gets half of the energy that was originally in the sine wave, and the two sidebands get a quarter of the energy that was in the sine wave. So a quarter, a half, and a quarter. And if we add them together, back together, then that's one. So all that to say that we're not losing energy, we're just like spreading it in the spectrum in the two sidebands and in the center frequency. Okay. So if I was drawing the spectrum of that, if my center frequency is here, it's half of the original energy, and then the two sidebands are going to be here and here, and it's going to be a quarter of the original amount of energy that I had in my input signal. Okay. And then what happens is that if my center frequency is here, I'm going to call it FC. Okay. So this sideband here is going to be equal to FC plus FM. And FM is the frequency of the modulator. So the frequency of the tremolo. So in our case for now, if the frequency of the sine oscillator that we're modulating is 1000 hertz and the frequency of the modulator is 300 hertz, then this sideband here is going to be 1300 hertz. Okay? And this sideband here is going to be FC minus FM. Okay? So it's going to be 700 hertz. Okay? So that's pretty cool. In terms of optimization, it's interesting, because basically with two sine waves, we were able to make three. So that's it's pretty good. And that's the whole principle behind frequency modulation synthesis. Because with frequency modulation, it's not only three, but it's way more than that. And so that's why FM was so successful. Because with only two oscillators, you were able to create a lot of harmonics and a lot of sine waves. So it was cheap to make those devices, or not too expensive, at least. Okay, but then, so we're sending a sine wave to that, but what happens if we send something else than a sine wave? A sound that is more complex, a sound that has more than one harmonic, one sine wave in it. What happens?
The same thing happens to all the harmonics.
Absolutely, the same thing for all the harmonics. So if I send the sound of my voice in this effect here, then all the single harmonics in the sound of my voice are going to have that will happen to them, So that will create a very interesting effects, because I'm going to significantly increase the number of harmonics in the sound of my voice, and I will be able to control that with the frequency parameter that I have here. So actually, let's try that. So I'm going to put the depth back to 0. So the depth here, of course, will control the amount of energy that I send in the sidebands. And I can see that the energy gets spread out, right? Because as I increase the depth, I can see that the sidebands increases, right? But the center frequency decreases. Okay? And just as a reminder, the scale is in dB, right? And because it's in dB, things increase very, very fast at the bottom here, but then the range that I have here is much bigger than the range that I have here, basically. So that's why it goes up very fast here, and not as fast at the top of the graph. Okay. So what I'm going to do to my Faust code is that I'm just going to remove the sine wave so that I create an input, and that this input gets sent to the tremolo. Okay, so I save that. And I'm probably going to have to change the routing of things in Jack. So what I want to do is to send the sound of my system to Faust Live. There we go. That's the sound of my voice. So, so all these things are the harmonics in the sound of my voice. So you see that there are actually a lot. So for now, I'm not applying any tremolo or any ring modulation, but I'm gonna do it now, and we're gonna look at the spectrum of my voice changing as I do it. So, well, it's a bit hard to see, I guess, but because it's very dense spectrum, so the harmonics are very, very, very close to each other. But something like a triangle way for you? I could do a triangle, yeah, sure, but okay. Okay, it's not. But if I change the frequency, you'll hear it. Yeah. So I will try with a triangle wave, so that might be a little. Yeah. Okay, so to get a triangular wave, I'm going to import a new library. And this library is called oscillator.lib. Okay. And in oscillator.lib, I should have triangle. And triangle takes up one argument, and it's a frequency. So I'm going to put a frequency of 1000 hertz. And I'm going to save that. There we go. Where is it? So I have a triangle wave. The triangle wave has, well, already has more harmonics than a sine wave. But yeah. Yeah, here we go. Beautiful.
Very smooth.
Yeah. Okay. So that's ring modulation. It's very basic. It's been heavily used by guitar players in the 50s and in the 60s because that's actually an effect that is pretty easy to implement on the analog side, because you're just basically changing the gain of the input signal with some kind of oscillator, and designing an electronic circuit for that is not very, very hard. So, yeah, yeah. So, yeah, it's pretty cool. So, it's very close to another family of yes. So that's the thing. So the flanger is part of a big family of audio effects, that are all based on the same on similar principle to this one. But so the chorus and the phaser, for example, are well, we're going to study them a little bit later during the workshop, and they are actually more complicated than that. So, because they involve using delay, which is not the case here. Here, we're just doing amplitude modulation. So, yeah, we'll make a flanger. We'll make a flanger where we use delay, and then I don't think we'll make a chorus or a phaser because those are a little bit harder to understand in terms of the math behind it. I don't want to go to I don't really want to do math basically this week, so flanger, you don't really need to understand what the maths are doing, but to understand a phaser, if you don't really understand the math behind it, it's kind of hard to understand intuitively what's going on. So yeah, we'll do that maybe later this afternoon or tomorrow morning. So. Yeah. But yeah, that one is the ring modulator. Any other questions? Okay, good, perfect. So, well, now that your brain is warmed up, we're gonna do a small exercise. What we're gonna do is that we're gonna modify this guy here so that we're gonna make a stereo ring modulator. But it's gonna be a weird stereo ring modulator. I want you to make a stereo ring modulator where we use the sine wave here to change the panning of the sound, okay? So, so you want to reuse the pattern that we made yesterday, right? And basically change the position of the slider automatically on the software side with a sine wave. So that we do something like, and that if we go very fast, we do, and then it's going to be very, very unpleasant to listen to that if you have headphones, because your brain doesn't really like when you do things like that, okay? So, so what I want you to do is to reuse the pattern from yesterday. The code is on the website. If you lost it, it's right here, okay? So you reuse the pattern, except that this time, instead of using a slider to control the position of the sound in space, we want to use a sine oscillator. And the two parameters that we want to have are the same than the one for the ring modulator. We want to be able to control the depth, okay, and the frequency of the oscillation, okay? So if depth is 0, no panning. We hear the same amount of sound on both the left and the right channel. If depth is 1, then all the energy of the sound gets transferred from one side to the other, depending on the speed of the oscillator that you use. Okay? Does that make sense? All right. Good luck. So I'm gonna comment that out for now here, so that we kind of start over with something cleaner. Okay, so I'm going to create a new process. Okay. And I'm just going to create a function that I'm going to call stereo ring mod. It's usually a good practice to create functions for everything that you do, you know, because basically stereo ring mod is an object. So, so just create a function for it, because that's just a good practice. Okay.
And reinforcing it, then, if you find you have lots of lines in your function, you're probably doing it.
Oh yeah, that's true. Yeah. Just try to make nice little objects for everything that you do. It's what good programmers do in general. In general. Yeah. Okay, so I'm going to create a new function that I'm going to call stereo ring mod. This function is just going to be a pattern, right? So I'm just going to copy that, okay? And I'm going to paste it in here, okay? So it's going to have local variables. And one of these local variables is going to be the pan variable that I'm using in here. So I'm going to, Emma, is it working or? Okay. Okay, so I got the pan variable. So we said that we basically want to modulate the pan variable with the sine wave of the tremolo, right? So in the tremolo function that we created before, and that is on the website here, the tremolo function is taking an input, right? Because of the multiply that we have here. So we're multiplying the input by this operation in here between the parentheses, right? we don't want to do that for our stereo ring modulator, right? Because we only want to take that, so this signal, the result of this operation, and modulate pan with it. So if we take the whole thing here and paste it to control pan, it's not going to work, right? Because it's expecting an input. So what I'm going to do is that I'm just going to take that. So only that part, and I'm going to paste it in here, okay? So now the stereo ring modulator is taking an input, splitting it into two different signals. One is multiplied by 1 minus pan, and the other one by pan. And pan is basically a sine wave, okay, with a certain frequency that we didn't declare yet, okay? And this sine wave is scaled so that its signal is in the range between 0 and 1. Okay? And if it's not in the range between 0 and 1, it's not going to do what we want. Or, well, in the case of the, no, it's not going to do what we want. We don't want to do that. Okay. And then we have the 1 minus here, so that if we change the depth to 0, the output of pan is 1. Okay? Cool. So pretty much almost have everything in here. The only thing we have to add are the frequency and depth parameters that we had here. I'm going to take the one from the ring modulator because those have the right maximum frequency for the frequency parameter, which was not the case of the tremolo. So, by the way, Faust doesn't really care about where variables are declared. So you can, you can call something before you actually declare it if you want. So, we could put frequency and depth after pan if we wanted. I mean, you should avoid doing that because it's not very clear for someone who tries to read your code. So it's probably better to just do things. Just do things like that, okay? So now if I save that, I get an error. Happens sometimes. So I probably forgot something somewhere. What did I do wrong? So that's one of the main problems with Faust. The Faust debugger is not very, I'm missing a parenthesis, yeah. Yeah, I'm missing a parenthesis. Let me just check, what did I, oh yeah, there we go. Okay, so I'm gonna send white noise to it, to my stereo ring modulator. Yeah, it's probably a little bit too fast. There we go. If I replace that by a triangle wave, should be funny. Okay, so it's kind of a weird effect to do because then you kind of do amplitude modulation at several levels here because you're doing amplitude modulation on the software side, but you're also doing amplitude modulation in the room itself, basically. So you probably get like interesting interactions, and if you use headphones for that, it's horrible to listen to it because then you're really yeah. So Exactly, that's the thing. Well, there are sidebands created in here because, but at half the rate at what they're supposed to be created, because it takes one period to go from one side to the other, right? But you're also creating sidebands within the room because there is the interactions between the two speakers. Yeah. So if we really wanted to have an accurate spectrum, we'd have to put a microphone in the room and look at the spectrum on what is created, because it's probably more than what we actually get on the computer side. So it's a funny effect. Yeah.
Can you run that code again? Sorry.
Sure. Sorry. Right. Explain it, you mean, or just?
Yeah, just run.
Oh yeah. Okay. Sorry.
Just run that code and make sound.
Sure.
Can you slide the frequency up to?
It's the collision of the air particles.
Yeah.
Running the sound waves. Not the actual waves from the speaker.
Mine stuck at the 601 and it doesn't go.